Chapter 3, Section 3.2, Logarithmic Functions and their Graphs. Here are the section objectives. And we'll look at the definition of a logarithmic function with base A. Logarithmic functions were introduced as a way to undo an exponential function. And so what you can see here is the function log base A of x is true if and only if x equals a to the y. So I'm going to write that separate. This is our exponential function that we are more familiar with. And here's an if and only if arrow. If and only if y equals log base A of x. So you can see here, here's your x, base A to the y equals y. You can see the components are in both of the equations. Just the one on the right has a log, the one on the left has an exponential component. So the thing is with these, they are interchangeable. So the log function was introduced in order to, undo an exponential function, or in this case, rewrite it. So as we go through and talk about the different examples and ways to use a log function, I'll be referring to this a lot, going back and forth in between these forms. So if you have a log equation, you can rewrite it and it's the same equation in exponential form, and same vice versa. So here it says, evaluate each logarithm with the given x value. So I'll start with part A. It says log base 2 of 32. What does that equal? What does that equal? Now, I am going to say it equals x because I don't know what it equals, and it just allows me to complete my equation and try to solve for x. So here I have a log equation. I can switch to an exponential equation, like I talked about on the last slide. If I switch it to exponential equation, it's a little bit easier to think about and figure out what we're trying to solve. So I like to loop around. I start with 2 to the x equals 32. So basically when I'm, trying to figure out what this equation equals, I can ask myself 2 to the what equals 32. And if I can figure out that exponent, then I know the answer to this log expression. So 2 to the what is 32? Well, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 would be 16. So 2 to the 5 is 32. You can take that and guess and check on your calculator if you want, but that's how we would get that answer to that expression. All right, part B is log base 3 of 1. What does that equal? So same deal, I'm going to rewrite it. 3 to the x equals 1. I do the loop so that I write it in the correct order. So I first write the 3, then the exponent is the x, and then loop around, and the last thing you write is the 1. It's just a little trick I use when I'm rewriting. So 3 to the what is 1? Well, anytime you raise anything to the 0 power, it's 1. So that one is 0. All right, part C, over here, log base 4 of 2. So I'm going to switch that. Let's see, it'll be 4 to the x equals 2. So 4 to the what is 2. Now that's not as easy because it's not an integer here, a positive integer like we've had in part A, or 0 like we had in part B. So I'm going to have to go back to how I solved exponential equations, and I'm going to try to use that same base strategy, or the 1-to-1 strategy. Since I have like a 2 to the 1 on the right, I'm going to try to get that to be 2 to the something on the left. So I can take out the 4 and I can rewrite it as 2 squared to the x. So that's this part, I just rewrote it. I'm going to keep my 2 to the 1 on the right. So when you have the same base on both sides, we can disregard that base and just look at the exponents. So to the 2 to the x, I'd have to multiply those exponents. So that would be 2x. On the right, I only have 1. And then I have this little equation that I just have to solve. So how do I solve that? You know, divide both sides by 2. So x will be 1/2. All right. Last one is part D. And part D would be log base 10 of 1/100th. All right, so I wonder what that is. I will switch forms. 10 to the x equals 1/100th. And try to figure that out. I'm going to use that same base strategy again. I'm happy with the left side, 10 to the x. On the right side, I'm going to rewrite 100 as 10 squared. So I'm looking at a base of 10. The issue is right now on the right side, the 10 squared's on the bottom, and I'd like it to be on the top. So I'm going to move that, 10 to the 2, I'm going to move it to the top. So on the left, I have 10 to the x. On the right, I have 10 to the -2. Remember, when you move something from the bottom to the top, you switch the sign of the exponent. So now I'm here, and I can cancel out or not cancel, but disregard my bases. So x equals -2. Here's the typed out solution for parts A and B, and C and D. All right, properties of logarithms. These are things that come up often that are good to know. Here we just had that one, log base anything of 1 will always equal 0. And that's just because that exponent of 0 always makes it equal 1. If your log base A of A, if those match, it will always equal 1. Here's another one where if you switch forms, this is what it looks like. And then this one-to-one property, it says property. If you can cancel out your log base A's or disregard your log base A's and just view the x equals y if you're solving an equation. All right, when we're looking at graphs, in order to sketch the graph of a log function, we are going to use, the facts that the graph of an inverse function is a reflection over the line y equals x. So here, these are inverses of each other. So if I graph 2 to the x, and then I reflect it over the line y equals x, which is the inverse line, I will get the graph of log base 2 of x. So I'm going to go ahead and that's my x and y axes. Here's my line y equals x. Okay, and then I'm going to graph 2 to the x. If you've forgotten, what that looks like, you can make yourself a little t-chart. 2 to the -2 would be 1/4. 2 to the -1 would be 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. -2 1/4. -1 1/2. 0 1. 1 2. 2 4. So this is the graph 2 to the x. That's in red. All right, now I'll switch to blue. I'm going to reflect all of these points across the inverse line, the y equals x line. So let's start with this one. There's that. And actually, it's hard for me to see the reflection accurately. So also with inverses, you flip the points x and y. So I know it's going to be x equals 1/4, y equals -2. So 1/4 down -2, 1/2 down 1, and then 2, 1, and 4, 2. Okay, so that is how I get the graph of log base 2 of x. Here is the same thing I just did. There's your t-table, and then there's a nice, computer-generated graph of those functions we just did by hand. All right, here are the properties of a log function: domain, range, intercepts, etc. All right, one of the most commonly used types of log functions with a certain base is the natural log, and that means you have a base of an e. So whenever you see natural log, that means base e, and there's a shorthand way to write it, and it is ln of x. So on calculators, if you see the ln button, it just means log base e. It's called the natural log function. So a calculator can carry out a lot of log functions, depending what type of calculator you have. And so if I was going to do all these, if I was going to evaluate them, natural log of 2, I would type in natural log of 2. My calculator would spit out a function. Here, natural log of 0.3. You could type in all those, see what it gets you. Here is the answers if you want to check and try it yourself. You can't take the natural log of a negative number because it's outside of the domain, so you will notice you get an error for part D. And then similar properties with the natural log as we had to the general logs. All right, so we have an application here. It is a human memory model. Students participating in a psychology experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took a retest to see how much of the material they remembered. So they, learned something in a lecture, and then they had to take a test every single month to see how much they were remembering over time. So here, our time will be from 0 to 12 months, right away, and then after a month, 2 months, 3 months, up to 12 months. And then here's the function that they got that modeled the data. So it asks you to find the average score right away, which t equals 0. So that would be the original exam. So I'm going to have up here, here's my function. For part A, I'll plug in 0. So f of 0 would equal 75 minus 6 ln of 0 plus 1. Type that in your calculator, see what you get. So it looks like, guessing here, the average score we have right away is 75. Then we'll plug in 2 and we'll plug in 6. So for part B, we would get f of 2 equals 75 minus 6 ln of 2 plus 1. And then C, we get f of 6 equals 75 minus 6 ln of 6 plus 1. And type all those in and see what you get. What's the average score after 2 months? It has decreased from 75 to 68, so people have forgotten some things. And then after 6 months, we're down to an average score of 63. Again, people are forgetting some things.